Hi all. Today we're going to talk about some Proton NMR examples and particularly focus on splitting and symmetry and those sorts of considerations. So if you look on Canvas, you'll find this worksheet, Proton NMR Examples number 1, and we're going to go through this and try to make some light of it. So in our first example, propose structures for this compound with a formula of C4H9Br. Now, the first thing we'll want to do anytime we're doing a structure is to look at degrees of unsaturation. In this case, we don't have any degrees of unsaturation, so that we know it's not a ring shape, there's no alkenes, there's nothing like that. So what we can start to think about is the basic format. We could have 4 carbons in a row as our backbone, with the bromine connected somewhere along those lines, or we could have a branched structure. And so we want to look at a couple of things on this NMR. First, we have 3 signals. We have the signal around a shift of 1 part per million. We have a signal around 2 parts per million. And we have a signal at about 3.3 or 3.4. Since we only have 3 kinds of signals here, we know that we don't have 4 carbons in a row. Because if we had 4 carbons in a row with the bromine connected someplace, that would indicate that we should have 4 distinct types of carbons in this molecule. And we don't. We only see 3 signals. So we know that this isn't right. The other piece of information we have that suggests that we have a branched structure is in the integration. Now, from the reading, we know that integration tells us how many hydrogens we have that contribute to a certain peak, or at least the ratio of those hydrogens. Now notice in our formula we have 9 hydrogens to account for. We have 6 hydrogens making up the shift at 1 ppm, 1 more hydrogen making up the shift at 2 ppm, and 2 hydrogens at 3.3 ppm. So that gives us our 9 total. What we'll see here is that we have a peak with a relative area of 6, representing 6 hydrogens. That almost certainly means that we have 2 methyl groups, 2 CH3s that are chemically equivalent. So from that information, I would propose a backbone that looks like this, where I have 2 methyl groups. And then we just have to figure out where the other hydrogen and bromine atoms are. So if we draw out our 2 possibilities here, we could have this backbone structure where I have the bromine on the central carbon, or I could have a hydrogen on that central carbon and bromine on the end. Those are the only 2 structures you can come up with that fit the 2-methyl sort of a structure as well as this formula. Now notice that if it were the structure on the right, we would have 3 equivalent methyl groups. And so that peak that showed up as only 6 hydrogens would actually show up as 9 hydrogens. We'd have only a single peak on this spectrum, and it wouldn't look at all like we see up above. So what we're seeing up here is, in fact, the structure that's sort of in the middle of the page, this branched structure that has the bromine at the end. And so what we have here are 2 equivalent methyl groups. Those are giving rise to our doublet peak here. It's a doublet because those 2 methyl groups have only one neighbor, the central hydrogen in that molecule. Remember that splitting only works, or is only apparent, when we're talking about being 1 carbon away, or what some books will say 3 bonds away. So hydrogen to carbon, carbon to neighboring carbon, carbon to hydrogen. So we have a 6 hydrogen peak split into a doublet. That would be the result of those methyl groups. We then have also a 2 hydrogen peak that's going to be seriously shifted because it's connected directly to a bromine. So we should expect that to be up pretty high, and we do see that here. That's going to be our 3.3 shift, 3.3 ppm shift. That peak is also split into a doublet because of that 1 neighboring hydrogen, the one in the middle. And so we have our 2 hydrogen doublet there. Now, the one in the middle, this hydrogen in the middle, gives rise to this whole mess of stuff around a ppm of 2, or delta shift of 2 ppm. And this is what we would call a multiplet. This is the result of complex splitting. If we wanted to try to count up how many peaks we should see, quote unquote should see, this hydrogen peak would be split into 7 peaks based on the effect of those methyl hydrogens. Remember that 6 equivalent hydrogens, the n+1 rule would say 6 hydrogens splits us into 7 peaks. So we'd be split into 7 peaks already based on the methyl groups, but then each one of those 7 would be potentially split into 3 peaks as a result of the CH2 protons. So 7 peaks each split into 3 peaks, we're talking potentially 21 peaks. Now, we would basically not ever see 21 peaks here because there's some overlap and the resolution isn't going to be perfect. But that middle signal is our 1 hydrogen multiplet. And so all of our available evidence fits this piece of information. That middle structure is right. Now we can use the same kind of logic down below. C4H8Cl2, again, we don't have any unsaturation, so we know that we're talking about an alkane or alkyl halide in this case. We could imagine 1, 2, 3, 4 carbons in a row, again, is a possibility. We have 2 chlorines to place in this case, so things will be a little bit more interesting, but again, we should have, if we have 4 carbons in a row, 4 distinct signals. And in fact, that is what we see. We've got a signal at 1.5, one at 2.1, one at 3.7, and one at 4.25. So 4 carbons in a row is going to make sense for us here. Again, I'll draw out a couple of possibilities. We have 2 chlorines to place. Okay? So we have a few formal possibilities. We could have both chlorines on an end. This would be predicted to give us one very shifted signal for the hydrogen that would be on that same carbon, and then a somewhat less shifted signal for the neighboring hydrogens, and then a lesser one and a lesser one, so forth. Okay, so this one might make some sense for us. We could have a chlorine on each end. This one would not make sense for us. And the reason for that is symmetry. Right? If we had a chlorine on each end and you can fill out all the missing valences with hydrogen, now we have symmetry in the molecule. And so the hydrogens here would match equivalent, would be electronically equivalent to the hydrogens there. And the hydrogens on carbon 1 and carbon 4 would be electronically equivalent. From this molecule, we would only get two signals. One that's quite shifted based on being connected to the chlorine, and one that's less shifted for those middle hydrogens. So symmetry's got to be out. So let's say we have a chlorine on the end. 1, 2, 3, 4. We could have our second chlorine on position 2 or on position 3. And that's it. Those are the only remaining possibilities. And so if I fill in all of our hydrogens, sorry, this is a little bit cramped. I'd like to blame it on the digital drawing, but this is actually how I draw these when I work on them. I draw out my chemical, carbon structures first, and then I kind of fill in my hydrogens to see what should go where. Okay, now we want to look at our integrations to see kind of if that can help us out. And again, we see all of our hydrogens are represented. We have 8 total. And what I'm going to do is I'm going to go ahead and just translate these numbers over to the diagram so that we can look at them. So my peak at 1.5 is a 3 hydrogen peak. My peak at 2.1 is a 2 hydrogen. My peak at 3.7 is also a 2 hydrogen. And my peak that's most shifted there is a 1 hydrogen. It's based on those integration numbers. And so 3, 2, 2, 1, if I look at all of the drawings that I've made here, they all are a 3, 2, 2, 1 kind of a setup. So that makes sense. We're in good shape so far. Now, how do we distinguish between them? Well, this is where the splitting pattern might come in handy. And in particular, we know that the 1 hydrogen peak must be because of the, the single hydrogen. So this one I'll underline it in all three cases. That's my one hydrogen peak right here. So that one's pretty shifted, right? If we look in our shift tables, we're going to see that a hydrogen that's on a carbon that's connected to one halogen is going to be shifted pretty significantly. Two halogens, we might expect a higher shift. So, maybe that first structure with the two chlorines on the same carbon, that one might be out. But it's not super conclusive in my mind. I'm not sure what the two hydrogen signals are, right? Because I have two carbons that each have two hydrogens, so it's a little bit unclear. But I do know that the 3 hydrogen signal is my methyl group. And so let's look at my possibilities for the methyl group. Notice that the methyl signal I'm seeing is split into a doublet. And that means the carbon next to the methyl group must only have one hydrogen on it based on the n+1 rule. So I have to have a methyl next to a CH. The only way that's going to happen in a straight molecule is if that CH also has a chlorine on it in the last valence. So that tells me that the first structure I drew is out because I can't have a CH2 next to the methyl group. Likewise, the second structure I drew is out for the same reason. And so now we're left with the third structure down here, which I think has to be right because it's the last one we have, but let's analyze it just to be sure. In this case, I should have a 2 hydrogen signal based on that CH2 group that should be pretty shifted because it's connected to a chlorine. And it should be split into a triplet because it has 2 neighbors, the CH2 next door. I have my 3 hydrogen signal that should be a singlet. And it's going to be a little bit higher shift than I'd expect for a normal methyl because it's one step away from a chlorine, but not directly connected, so not too bad. So far I'm doing okay. My 1 hydrogen peak here should be very shifted, again up pretty close to the 2 hydrogen triplet because it's connected to a chlorine. Its splitting pattern is going to be a mess, right? It's going to be a multiplet. I'm going to be split into 4 peaks based on the methyl group, and each of those 4 split into 3 based on the CH2 to the left. So I'll have a 1 hydrogen multiplet. And I might predict 12 peaks at 4 times 3, but really we'll just say multiplet. And then my other CH2 group, 2 hydrogen group, it's going to be moderately shifted. It's not directly connected to a chlorine, but it's in between 2 carbons connected to chlorines. And it's also going to be a multiplet. When I look at it, it'll be shifted, split into 3 based on the hydrogens to its left, and then each of those split into 2 based on the hydrogens to the right. And so 3 times 2, I'd expect a 6-plet, I guess I could say. I don't know, a multiplet with 6 peaks on it. And so that could be the end of the story, right? Now, what I want to look at here is what's going on with that CH2 group. So remember, this is the not quite shifted one, or not seriously shifted one. That's going to be this guy here. So why am I seeing only 4? Well, notice that those hydrogens, the CH2 hydrogens to the left and the CH hydrogen to the right, are both in very, very similar electronic environments. They're both sp3 carbons. Those carbons are both connected, or each connected to 1 chlorine. And so what I'm seeing here is basically the coupling constant for each of those splitting events is going to be very, very similar. And so essentially what that's telling me here is that if I had a high enough resolution instrument, I might see a 6-plet, but what I'm really only seeing here is 4. So this is the only structure that matches the data, particularly for the splitting of the methyl group being split into a doublet, but everything else is justifiable. And if I were to label things, I'm running out of colors here, so let's go with orange. If I were to label things based on which signal is which, or maybe orange is too similar to what I just did. Let's go with purple. What I would say is my 1 hydrogen peak is going to be right there. The 2 hydrogen peak right next to it would be the one that's connected also to a chlorine. The other 2 hydrogen peak is going to be the one in the middle. And the 3 hydrogen peak, of course, is my methyl group. So that one's a little bit tricky, but there's only one structure that fits. The only discrepancy is that 4 versus 6. The other significant kind of question that you'll see is how could you use Proton NMR to distinguish between each pair of molecules shown? And, you know, the molecules that I chose here are isomers of each other, so they have the same chemical formula. What you'll want to think about in these kinds of questions is doing what I just did with those upper questions when I was sort of justifying the answer. Go through and say, what kinds of signals should I be expecting and where should they be? And I'll just sort of give you the high-level view of this first one. I do see symmetry in this molecule, and so I would expect only 2 signals from that molecule, whether I'm talking about carbon NMR or in this case proton NMR. Whereas in the other one, I don't have symmetry, and so I would expect 4 different signals for that molecule. You can predict where they should line up, and you can predict the splitting here. The answers to those questions aren't necessarily super relevant to answering this question, but just by way of giving you the short version here, in this molecule I would expect 2 signals, a 6 hydrogen signal, right, because of symmetry, both methyl groups are the same, a 6 hydrogen signal that would be split into a triplet, because each of those methyl groups only has a 2 hydrogen neighbor, 2 plus 1 is 3, triplet. And I'd expect a 4 hydrogen peak that would be split into a quartet because the CH2 has 3 neighboring hydrogens. So 2 signals, a triplet, and a quartet. I'm not going to try to predict delta numbers here, but I would predict that the triplet would be closer to 0 because it's further away from the oxygen. The quartet signal should be shifted a bit more. Over on the far side, the second example, I would have a 3 hydrogen. Notice it has no hydrogen neighbors, so a singlet. It should be pretty shifted because it's next to an oxygen. Pretty close by, I should also have a 2 hydrogen. This one has 2 neighbors, so a triplet. I expect that signal to be pretty close to the singlet I just mentioned because they're both connected to an oxygen. Over here, the easy one, I would have a 3 hydrogen, again, triplet, right? And it would be pretty close to where methyl should be, so a sub 1 ppm kind of a number. And then I'd have my 2 hydrogen multiplet in the middle. And again, if I wanted to get fancy, I'd say maybe it'd be a 12-plet, but probably not in reality. It'd be split by those 2 sets of non-equivalent neighbors, the CH2 to the left and the CH3 to the right. And I would expect this one to have an intermediate delta value just because it's kind of closer to an oxygen, but not really close. So somewhere in the probably 1 to 2 ppm range. Same kind of logic can be done in part D, and I'm going to let you figure that one out. The answer is down on the next page, and it's fairly well explained. But these are the kinds of questions that you'll want to practice with. And there's lots of practice to be had in the textbook. There's practice to be had in other textbooks. I can give you as many practice examples as you want, but the real big concept here is to think about symmetry, equivalence, the shifting value itself, and splitting. So with that, I'm going to call this a day, and we'll definitely talk more about splitting and Proton NMR and everything else, but get your practice in and let me know how I can help. Good luck.